Hello there.
We begin, of course, with the idea of the Carnot Engine, right? Named after Sadi Carnot, a French physicist and the father of thermodynamics, essentially. Carnot stating that no engine is more efficient than the Carnot engine. Now, the idea behind this is, it may sound like it's cocky of him to say, but the idea, his theory and his idea behind this is a four-stage cycle that could be reversible, meaning there is no efficiency lost. It would go forward and it would go backwards. All of the heat ends up becoming converted to work, and then therefore work could be converted back to heat. It's ideal. It's theoretical. Is it realistic? Let's talk about it. So, any efficiency of an engine would be calculated as follows. Efficiency could be work over QH.
Perfect.
Or efficiency could be
I think I need a hug.
QH minus QC over QH. Or it could be TH minus TC over TH. Okay? Be aware of that. So we can go ahead and find those efficiencies all the same. Problem 1. We're given an efficiency. Don't forget to convert your percents to decimals. So that's going to be 0.45. The engine absorbs 800 joules of heat per cycle from a hot reservoir. So it's absorbing this from a hot reservoir. Okay, in other words, this is your QH. We want to find out how much heat is expelled per cycle going to QCs. Please be careful as we add more and more ideas to thermodynamics. You need to be careful and keep track of what is being given and what is being asked. Okay, so we have here 0.45 is equal to 500 minus QC over 500. We multiply both sides by 500. And then if we go ahead and solve for QC, we end up getting 275 joules. Next, an engine absorbs 2,000 joules of heat energy. It's absorbing, right? It's absorbing. So be aware as we do some of these problems, we're not going to tell you if it's a hot reservoir or a cold reservoir. You need to know, you just got to get a feel for this. So if it helps to make a drawing, make drawings. But if an engine is absorbing heat energy, it only absorbs heat energy from a hot reservoir, never from a cold reservoir. Okay? And it is 600 joules of work. To determine the efficiency, we would this time do the work over QH formula. Notice that efficiency is unitless. You can tell right here that the units cancel out. And putting this in the calculator, you get 0.3 or 30%. So this engine is 30% efficient.
Here we go.
So, second law is really about randomness, about disorder, okay, about entropy. And the greater the energy of an object, the greater the amount of motion of the atoms and molecules. But as time passes, there's a waste energy that is heated, and this contributes to disorder in a system. So the second law of entropy is about disorder. It's about measuring that disorder. Okay?
You lose.
So the idea here is that Carnot states that no engine is more efficient than a Carnot engine. In other words, nothing can be as good as 100%, right? And so what you have here is you have people like Clausius and Kelvin and mathematics just in general that talks about entropy and that every system has entropy, okay? This means that nothing is 100% efficient. Nothing, all right? There will always be waste energy. So this waste energy, right, and the way that things go into disorder. Think about it. You buy bread. Does it last you forever? No. Entropy, okay? Everything goes to a state of entropy. The entropy of the universe tends to a maximum. There's nothing you can do to change an entropy of a system. Think about this. Think about your room, right? And it's a mess, right? And that'll be our secret. But your room is a mess. If you're told to clean it up, the process of cleaning up your room introduces more entropy. So the fact that your room is already in disorder, think about the heat energy that you have to exhaust. Think about all the movement you're doing. Think about all the things you're moving. Think about the dust you're moving. Think about all the work is being done. In order to make a system go back into order, you must contribute to heat of the universe. And in doing that, you contribute to more entropy. if you want a good argument for not cleaning your room, it contributes to the entropy of the universe.
Brothers and sisters, the earth is changing, and we must alter our habits before it is too late. We need to go green.
I'm afraid we don't understand, Brother
Climate change. It's happening all around us. We have to reduce our carbon footprint or our children will never see polar bears. Because they'll all be dead.
The children or the polar bears?
Both. Children and polar bears are particularly susceptible to climate change.
But, Brother Jebediah, what do you propose we do? We don't even use electricity.
There's always something you can do, Sister Obadiah. For example, how did you all get to this meeting today?
We walked, because we don't drive cars. So we're already helping.
Ah, but walking produces friction, and friction creates heat. Your cavalier walking habits are raising the temperature of the entire world.
But how do you go more green than walking?
You can't.
Well, that's exactly my point.
No, I mean you can't walk. If we would stop walking, we could eliminate 0.05% of friction-based heat. And that's a conservative estimate.
Surely you walked here today, Jebediah.
Actually, I haven't moved from this spot in 3 days.
Brother Jebediah's right. I know in the heat of the sun, when I'm wearing my long-sleeve black clothing, plowing my fields, doing my Pilates or hot yoga, well, I begin to sweat.
My word, man, don't fan yourself. Great. You made me walk.
But why can't I fan myself?
Climate change. We can't go fanning ourselves willy-nilly. It'll alter the temperature.
All this friction nonsense, it doesn't seem very practical.
What's the matter, Brother Hezekiah? Is the truth too inconvenient for you?
A little bit, yes. According to you, we can't even walk around without the earth melting beneath our feet.
Very well. Bring it out.
Jebediah, I don't understand.
Go ahead, Brother Hezekiah. Shoot it. Your actions have ensured that it's as good as dead.
I can't.
Are you sure? Brother Jeremiah used a lot of friction to get it here.
No, I'm not a monster.
Very good, Brother Hezekiah. Welcome to the cause. Oh, careful. The friction. Air 5.
So the entropy, the change in entropy, or the measure of disorder in a system, is equal to the heat divided by the temperature. Now, it's important that your temperature be in Kelvin, okay? The units for the change in entropy is going to be joules per Kelvin. If an engine has less than 100% efficiency, what does this mean? Give one answer in reference to Carnot and another in reference to entropy. I want you to really think about this.